I want you to picture a specific kind of colleague. Let's call him the perfect student. I sat down with him recently to go through a massive stack of documents, thousands of pages of technical data. I asked him a simple, specific question about a conclusion found in the final chapter. You would expect a genius researcher to flip to the index, scan the headers, or jump to the relevant section. But he didn't do that. Instead, his demeanor changed completely. He locked his eyes onto the very first word of the very first page. He started reading linearly, word by word, with an intense, almost manic focus. He was obsessively cross-referencing every single the and but with every other word he had already read. He looked exhausted, practically vibrating with the effort, telling me that to understand the answer on page 500, he had to perfectly memorize the relationships between every word on page 1. It was painful to watch. He was burning through energy, sweating, and wasting hours on a task that should have taken seconds. It was technically perfect recall, but it was agonizingly inefficient. And then it hit me. This wasn't just a story about a bad coworker. This is exactly, down to the mathematical code, how the world's most advanced AI models operate right now. Beneath the surface of ChatGPT or Gemini, there is a full attention mechanism that acts just like that exhausted student burning up to 80% of its computing power, just rereading irrelevant noise to ensure it understands context. But what happens when you finally teach that machine to stop reading like a robot and start skimming like a human? A new paper just stunned the computer science world by doing exactly that, and the results are about to make everything we know about AI speed look ancient.
That analogy, the perfect student, it's just incredibly precise. It perfectly captures this core, almost existential problem that's been at the heart of the transformer architecture for years.
It's been the bottleneck, the one thing holding everything back.
Absolutely, the single biggest limiting factor. So today, we're diving deep into the architecture behind that breakthrough you mentioned. Native Sparse Attention, or NSA. It comes from the researchers at DeepSeek AI.
And our mission here really is to unpack how they did it, how NSA manages to teach an AI to skim intelligently.
And critically, how it combines that algorithmic innovation with some really aggressive low-level hardware optimization. Because that's how it finally solves this infamous quadratic complexity problem. It's, fundamentally rewriting the economics of scaling AI.
Okay, let's start there. The mathematical catastrophe at the heart of it all, a quadratic bottleneck. For those of us who, appreciate efficiency but maybe aren't steeped in complexity theory, what does it actually mean when we say full attention scales quadratically? Why is that so disastrous?
Well, it all starts with the mechanism itself. The attention calculation is the core of the transformer. It's what lets the model weigh the importance of every single word that came before the one it's currently looking at.
Right.
In the standard setup, what we call vanilla full attention, every new query token has to access and mathematically interact with all the preceding keyed value tokens, all of them.
So if I'm on word number 1000, it has to check itself against the 999 that came before.
Yes. And if you're at the 10,000th word,
you check it against 9,999 others. I see where this is going.
Exactly. We define the sequence length as $. So the total number of interactions is proportional to nanta squared. That's the quadratic relationship, what we write as $.
So if you double the size of the document the AI is reading, say from 8K to 16K tokens, the cost doesn't just double.
It quadruples.
That compounding cost is what makes long context so expensive.
It literally creates a scaling wall. And that cost explodes in two different but equally critical areas. First is FLOPs, floating point operations, which is just the sheer amount of math. But the second, and this is often the real killer, is memory traffic.
Moving data around.
Specifically moving it to and from high bandwidth memory, or HBM. That's the super fast memory right next to the GPU. As your context length $, grows, that attention computation just completely takes over.
Can we actually put a number on that? Just how dominant does it get?
We can. When these models are decoding, so generating new text after you've given them a long prompt, at extreme lengths, like 64,000 tokens, the attention part alone eats up between 70 and 80% of the total latency.
70 to 80%. So almost all the time and energy is just spent rereading old data.
The system is spending maybe a third of its time thinking about the new word, and the other 2/3 or more just rereading the setup. The inefficiency is staggering.
And I imagine that translates into real-world costs, time and money.
Oh, absolutely. Think about a real scenario. You're trying to process one really long prompt, maybe a full code base or a massive legal document, let's say 1 million tokens. Even with a powerful 8 billion parameter model, That can take up to 30 minutes on a single top-tier GPU.
30 minutes for one query.
For one output.
That's not a scalable utility. That's a high-cost, specialized tool. And this is the whole point of the sparse attention movement, right? To break this Dork-Rana barrier and get to something closer to linear scaling, like Larracan-Zia, where you're only looking at the tokens that actually matter.
That is the theoretical holy grail. If you can go from squaring with length to just increasing linearly, the entire economic model changes overnight. But I should say, the road to sparse attention is just littered with failures.
Failures. I feel like we've been hearing about sparse models for years. Why was it so hard to get them to work in the real world?
It's this classic disconnect between theory and practice. A lot of sparse attention methods looked great on paper. They reduced the FLOPs count, so they were doing fewer calculations.
Which should mean they're faster.
Should. But when you actually ran them on a GPU, they were often slower. The wall clock time was terrible.
Why? If it's doing less math, how can it be slower?
Because a GPU is not a general-purpose computer. It's a highly specialized machine built for one thing, massive parallel processing. And it absolutely thrives on dense, regular, predictable matrix multiplications, which is exactly what full attention gives it.
Okay.
But when a sparse algorithm comes in and starts randomly picking and skipping tokens, you get these highly irregular memory access patterns. The hardware ends up just waiting for all this non-contiguous data to get loaded from HBM. All the time you saved by skipping the math is just completely lost waiting for the data to show up.
So earlier attempts were algorithmically brilliant, but completely ignorant of how the silicon actually works. They optimized the abstract math, but ignored the physics of the chip.
That's it, precisely. And that's the crucial context for NSA. It wasn't enough to just invent a new math trick. They needed a dual innovation, one that integrated the algorithm with a design that was explicitly aligned with how modern tensor cores and HBM actually operate. That realization is what sets NSA apart.
All right, so let's get into the solution. Native Sparse Attention. You described it as hardware-aligned and natively trainable. That phrase seems really important. It sounds like they built this from the ground up to solve both problems at once.
That's absolutely right. NSA is designed specifically for one thing: ultra-fast, long-context training and inference. And its core idea is what they call a dynamic hierarchical sparse strategy.
Okay, let's break that down.
Instead of treating the whole context as one long string of words, it first organizes keys and values into what it calls temporal blocks. Then it sends them to be analyzed by 3 specialized parallel attention modules. It's like creating a team of 3 different researchers, each one with a different way of reading the document.
I like that, a specialized team. So let's meet the team. What are the 3 pillars of NSA's efficiency? The first one is called Coarse-Grained Compression, or TextVaniken. What's its job?
The compression branch's job is to create a high-level global map of the entire context. It uses a learnable MLP, a multi-layer perceptron, to basically summarize sequential tokens. It might take a block of, say, 128 words and aggregate it into a single high-dimensional representation that captures the core meaning of that block.
So instead of my query having to check against 64,000 individual words, it can first check against maybe a few hundred of these compressed summary blocks.
You've got it. It's the AI equivalent of just reading the chapter titles and abstracts before you decide where to read deeply. The whole point of the TextVaniken branch is to capture those coarse-grained, high-level semantic patterns, giving the model this incredible global context awareness at a tiny fraction of the cost.
That's extremely efficient for just handling the sheer scale. But a summary can miss the crucial detail, right? The needle in the haystack. So how does NSA find those fine-grained details? This must be the second pillar. Fine-grained token selection or text cell?
Right. The selection mechanism is where the system gets really focused, almost like a laser. And it operates blockwise, which is a really important nod to the principles of Flash Attention for hardware efficiency.
So when a new query comes in, the model has to figure out which specific distant parts of the history are the most relevant and do it fast. How does it do that without just running full attention all over again?
This is the ingenious part. It actually leverages the intermediate results from the compression phase. Remember, that compression branch has already calculated some initial cheap attention scores against those block summaries.
Okay.
The model uses those low-cost scores to calculate an important score for the actual blocks of text underneath. And based on that, it only keeps the top-end, most relevant contiguous blocks of tokens for a full, detailed attention calculation.
Wait, that's a brilliant feedback loop. It uses the cheap high-level summary map to pinpoint the exact locations that need a deep read.
Precisely. And the fact that it selects contiguous blocks is so critical for that hardware alignment we keep talking about. The researchers noticed that attention scores have this property called spatial continuity. Basically, if one word is important, its neighbors probably are too.
So by grabbing a whole block instead of just scattered individual words,
You ensure that when you pull that data from HBM, the memory access is contiguous and predictable. That's how you keep the GPU's tensor cores fully utilized and humming along. It's the heart of the speedup.
if they picked random individual words, you'd get that chaotic memory access and the GPU would just stall. So choosing blocks makes the whole idea of sparsity hardware friendly. That's a huge piece of the puzzle.
It connects the algorithmic need for selectivity with the physical need for contiguous memory. Which brings us to the third pillar, the sliding window, or text one. This one's a bit more straightforward. It just explicitly pays attention to the most recent tokens, the immediate local context.
Okay, so you need a local window for things like conversation flow, immediate context. But why give it a whole dedicated branch? Couldn't the super smart compression and selection branches handle that?
This is a really subtle but important architectural decision. It's about training integrity. If you made the text skimped in and text branches also responsible for the easy local stuff, the model could get lazy. It could fall into what's called shortcut learning.
How so?
Local patterns are easy to learn. They're right there. The model could just get really good at predicting the next word based on the last few and never bother to learn the much harder long-range dependencies. By giving the Win branch the specific job of handling local context, it forces the other two branches to focus only on the hard problem, learning those complex high-level features across the entire vast context.
That's brilliant. It's not just about speed, it's about enforcing specialization to make sure the long context parts of the model actually learn about long context.
Exactly. And then at the end, you have to combine the outputs from these three branches. This is handled by what are called learned gating scores. Essentially, they're dynamic weights that the model learns during training.
So for any given task, the model learns how to open and close these gates. If it needs a high-level summary, it leans more on the compression branch.
Precisely. If it needs a specific detail, it opens the selection gate wider. And because it's a continuous learnable system, you can use backpropagation to optimize the entire strategy from end to end. This gives it a massive advantage over older methods that used fixed or non-trainable rules.
Okay, the algorithm is undeniably elegant. This three-pronged attack teaches the AI how to skim, summarize, and focus, all while keeping the hardware happy. But the proof is in the numbers. Let's quantify this speed revolution, starting with the most expensive part of the whole process, training.
The training speedups are, frankly, unprecedented for long context models. On an A100 GPU, processing a context of 64,000 tokens, NSA delivered up to a 9.0x speedup in the forward propagation pass.
9 times. Let's just pause on that. A research team planning a foundational model training run that was going to take, say, 100 days with full attention. They can now do that same work in just over 11 days.
Yes. It just completely changes the economics of AI development.
It accelerates the entire cycle of discovery. When you think about the grander vision, this kind of speed up for modeling complex systems, it directly helps us tackle hard technologies. Things like fusion energy, designing new materials, space infrastructure. Problems that were computationally out of reach become tractable.
And the backward propagation speedup was up to 6.0x, which is also huge for training. But the inference numbers, the decoding speedups, are even more dramatic.
What are we talking about there?
For decoding, which is where that memory bottleneck hits the hardest, the expected speedup at a 64K context is up to 11.6 times.
An 11.6x speedup. When you're dealing with huge amounts of context, that just dismantles the old limitations. You can now realistically analyze things that were impossible before.
And we know exactly why. Decoding is memory bound. For every new token you generate, the GPU has to load the entire key value cache from memory. With a 64,000 token context, full attention has to access all 65,536 of those equivalent tokens. NSA. It brings that down to just 5,632.
So the speedup is almost directly proportional to the amount of data the system doesn't have to move. The problem was never that the math was too hard. It was that the GPU was spending 90% of its time waiting for the data train to arrive.
That's a perfect way to describe it. It's called the low arithmetic intensity problem. NSA solves it by just not loading the data in the first place. It cuts the required memory bandwidth by over 90%.
Now let's go back to that critical phrase, natively trainable. You mentioned that older sparse methods were often inference only and they failed because they were just sort of bolted on at the end. Why is being trainable from the start so vital?
Well, it solves three huge problems. The first is what I'd call architectural bias. If you train a model for months to rely on full attention, and then at inference time you suddenly tell it to ignore 90% of what it sees, you're forcing it down pathways it was never optimized for. Performance almost always degrades.
So the model has to learn how to be sparse from day one.
Exactly. The second problem is non-trainable components. A lot of older methods use things like k-means clustering or SIMHASH to pick the important tokens. Those are discrete operations. You can't back-propagate through them, so you can't learn the selection criteria. They break the gradient flow.
Whereas NSA uses smooth, continuous components that allow the AI to actually learn its own best skimming strategy.
You've got it. And the third, and maybe most obvious problem, is training cost. The great irony of inference-only sparsity is that it does nothing to solve the massive quadratic cost of the training phase itself. NSA's real power is that it brings that linear scaling to the entire development process, and that efficiency unlocks the ability to analyze entire code bases, massive legal archives, global sensor data. It's about accelerating the reconstruction of the material world.
That is an incredibly powerful synthesis. But as we established earlier, even the smartest algorithm can run headfirst into the wall of silicon physics. And apparently, even NSA hit a hardware bottleneck. This is what led to the creation of Flash Sparse Attention, or FSA.
Where did the original vanilla NSA kernel get stuck?
It got stuck in the fine-grained selection mechanism of all places. Remember, NSA needs to load only the relevant KV blocks. The problem is because every single query token dynamically picks a different set of keys and values, the overall access pattern to the memory, while better than random, was still pretty irregular from the GPU's point of view. So if my query A needs blocks 10, 20, and 30, but your query B needs blocks 11, 21, and 31, across thousands of queries at once, the memory requests are all over the map.
All over the map. And the original NSA kernel was built with a specific loop structure. The outer loop went through the query tokens, and the inner loop went through the selected KV blocks for that query. This was designed to work with something called grouped query attention, or GQA.
Let's do a quick 30-second detour on GQA. Why is that so common in modern models?
GQA is a huge optimization. Instead of every query head having its own set of key and value heads, GQA lets a group of query heads share a smaller number of KV heads. The main benefit is it dramatically reduces the size of that KV cache, which is critical for running long context models during inference.
Okay, smaller cache, better memory use. Got it. So back to the problem with the original NSA kernel.
That original loop structure queries first was only really efficient if your GQA group had a large number of query heads. But the irony is, the most popular high-performance LLMs today use GQA with a smaller number of query heads to be even more efficient.
Why does having fewer query heads break the kernel?
It's because of the very strict rules of modern GPU tensor cores, those little math engines. To get max performance, the chunks of data they multiply, the matrix tiles, have to meet minimum size requirements. On a Hopper GPU, for instance, the dimensions have to be at least 8. If the number of query heads in the batch was too small, the kernel was forced to do something really wasteful.
What's that?
Padding. It had to add dummy zero-value data just to make the matrices big enough to satisfy the hardware's rules.
You're kidding. So it's adding useless data and doing useless math just to fit the shape of the chip? That completely defeats the purpose of being sparse.
Completely. The algorithmic win was being canceled out by a hardware loss. And this is where Flash Sparse Attention, FSA, comes in as the fix.
So what was the simple-sounding but obviously critical change that FSA made?
FSA is an optimized kernel, and it does one crucial thing. It inverts the loop order. Instead of queries in the outer loop, FSA puts the selected KV blocks in the outer loop and then processes all the queries that need that block in the inner loop.
That seems like such a small change on paper. Why does flipping the loop solve the whole padding problem?
Because while the number of query heads in a GQA group might be small, the total number of query tokens that need to access any given KV block is typically very large. So by looping over the KV blocks first, FSA guarantees that the inner loop always has a big batch of query tokens to work on. This large batch naturally meets the minimum size requirements of the tensor cores. No padding needed.
No padding, so you get maximum utilization of the tensor cores and clean, contiguous memory access. It's the engineering piece that makes the beautiful theory actually work at full speed on real hardware.
And the numbers back it up. FSA delivered up to a 3.5x speedup at the kernel level compared to the vanilla NSA kernel. End-to-end, that translated up to a 1.25x faster training time over the already fast original NSA. It's the difference between a cool research project and a product you can actually deploy.
I can see how that level of optimization is absolutely critical. But I have to ask, inverting that loop must create a new headache, right? If you're processing queries in the inner loop, a single query's final result is now being calculated in little pieces across many different threads. How do you stitch those partial results back together efficiently?
That is the new complexity, and they had to be very clever. If every thread just tried to write its partial result to the final output location in memory at the same time, you'd need these incredibly expensive atomic operations to prevent them from overwriting each other, and you'd lose all your speed gains.
So no fighting over the same spot in memory. What's the first step?
Step one is that the selection kernel calculates its partial results, the unnormalized attention scores, and writes them to a special intermediate buffer. And this buffer is smart. It's optimized to only allocate space for the valid queries, which saves even more memory.
And step two is the final assembly line.
Exactly. A second dedicated reduction kernel then swoops in. It reads all those partial results for a single query token, performs the final softmax normalization in a highly parallel way, and writes the final correct output. This two-stage decoupled design completely avoids those costly atomic operations and keeps the whole process incredibly fast.
It's clear that the combination of the NSA algorithm and the FSA kernel is a major engineering achievement. But this brings us to the most important question of all. You've created this incredibly fast skimming system, but did the AI get dumber in the process? Did this speed hack degrade the model's quality?
It's the million-dollar question, and the answer is, on the contrary, the evidence suggests it actually got smarter. They tested the NSA models, which were built on a 27 billion parameter backbone, against a standard full attention baseline across a whole range of benchmarks.
And what did they find?
Well, first, the NSA model achieved stable convergence during pre-training, which means the learning process itself was healthy. And on average, it either matched or exceeded the full attention baseline. In fact, it outperformed the full model on 7 out of 9 core metrics, including tough reasoning tasks.
It outperformed the model that was looking at everything. How is that possible? What's the implication there?
The implication is pretty profound. It suggests that the sparse mechanism itself acts as a kind of beneficial constraint. By forcing the model to identify and focus only on the most critical information, it's effectively learning to filter out noise. It learns what matters more efficiently, and that seems to translate directly to better reasoning. It's not just a speed hack, it's a cognitive upgrade.
That structure actually improves the outcome. Okay, so what about the ultimate test, the thing this was all designed for? Mastery of long context. How did it do on those brutal retrieval tests?
The results on the 64,000 context needle in a haystack test were, well, perfect. This is the test where you hide one tiny crucial fact somewhere in a massive document and ask the AI to find it. NSA got perfect accuracy across all positions.
That's the ultimate confirmation of that hierarchical design we talked about. The coarse-grained compression found the right neighborhood, and the fine-grained selection went in and found the exact address.
Absolutely. And when they moved to broader, more complex, long-context tasks with the long bench evaluation, NSA was superior again. It got the highest average score, outperforming the full attention baseline by a pretty significant margin, and beating all the other sparse methods they tested.
Where did it really shine in those complex tasks?
The biggest gains were in tasks that required synthesizing information across long distances. So multi-hop question answering, for example. And critically, it showed major superiority in code understanding tasks.
Code understanding. That requires tracking thousands of intricate dependencies. That feels like a huge strategic advantage. If your AI can process an entire code base or decades of legal documents 11 times faster and with higher accuracy, you gain a decisive lead. This positions whoever adopts it to just dominate future AI-driven industries.
And that strategic capability even extends into pure logical reasoning. They tested this by fine-tuning the NSA model on the ME benchmark, which is for complex mathematical reasoning.
Math derivations require holding these long, fragile chains of logic in memory. An inefficient attention system should just fall apart there.
That's what you'd think. But the NSA sparse models significantly outperformed the full attention model at both 8K and 16K context lengths. It was just better at holding on to those long logical dependencies.
So what does that tell us? Beyond just speed, it's the final validation. The natively trained sparse patterns aren't just a shortcut. They enable the model to more efficiently capture and maintain the long-range logical connections that are crucial for complex thought. By learning how to filter noise from the very beginning, NSA produces a model that is both exponentially faster and genuinely better at complex, long-range reasoning.
So this has been a really deep dive. We've seen how native sparse attention, supported by that crucial hardware optimization and flash sparse attention, managed to do two things that really seemed contradictory. Get exponential speed gains in both training and inference, but also achieve superior long context reasoning.
That is the core achievement. They've broken through that computational scaling wall of quadratic complexity, the dollar problem, and achieved true linear scaling. Algorithmically, NSA does it with that hierarchical, three-pronged approach compression for the big picture, selection for the details, and the sliding window for what's happening right now. And FSA was the absolutely essential engineering that translated that algorithmic beauty into raw wall clock speed. It solved those hardware bottlenecks, like the padding issue, with that elegant inverted loop. It's a perfect marriage of software and silicon.
And the outcome is profound. The speedups, up to 9x in training and almost 12x in decoding, they just radically change the cost-benefit analysis for developing and deploying the next generation of LLMs. This dual innovation unlocks the ability to efficiently analyze entire code bases, massive legal documents, global sensor networks. It accelerates the material world's reconstruction and resource optimization. The gains during the training phase speed up the whole cycle of discovery, fueling the exponential growth in AI capability that's going to redefine the future.